much for the invitation. And I'd like to thank the organisers for the invitation and for organising such a fantastic meeting. It's wonderful to be in Japan, and I bring greetings from NIST, from the National Institute of Standards and Technology in the US. So the talk today that I'm going to give will provide a little bit of information about NIST, for those who are not familiar with NIST, and then a summary of a few updates on quantum information science from NIST. So one might ask the question, why is NIST, where did the quantum information science program come from NIST? Well, NIST is a measurement science institution. We advance measurement science, that's our mission. And so quantum mechanics sets fundamental limits on the precision of measurement, and so therefore NIST has to be a leader in quantum. And so this is the history or the strategy, I guess, that's behind the quantum program at NIST. And of course, when you lead in a particular program, then that attracts research stars to your organization, and then the program sustains over a longer period of time. So where it all began for NIST in quantum was in atomic clocks. And so here are a couple of examples I'm showing on slides. On the left is Dave Wineland working with an early cesium beam atomic clock. And then on the right is Bill Phillips, who's working on laser cooling. So both of these researchers, of course there were many, these were the two leaders at NIST who worked on this particular programs. So Dave did the very first laser cooling of anything, of a trapped ion, and then Bill Phillips did laser cooling of an atomic beam. So these kinds of technologies underpinned the development of the quantum information science program at NIST. It started with clocks for us. So from clocks, there was the realization at NIST at a conference that was held in Boulder that one could use the same kind of trapped ion technology that we were using for building clocks, could also be used for quantum information science. And so in 1995, NIST produced the first quantum gate. So this is a picture showing, well, you can see Dave Wineland with a moustache, and next to him is a very young Chris Monroe. So this was the group that did the very first logic gate. They produced a truth table in a paper. I think this is probably the very first time that a truth table appeared in an atomic physics paper. I think most of us were kind of shocked by that. But since 1995, we've grown accustomed to this. Okay, so at the heart of the NIST quantum information science program is physics culture. So physics culture is the foundational culture of NIST. Physics underpins pretty much everything that we do, and we provide a lovely working environment for physicists, and that working environment has been rewarded in lots of different ways, including a bunch of Nobel Prizes. So here are some of the research stars from NIST. So at NIST, we started with these clock programs, but the quantum information science over 20 years, or more than 20 years now, has expanded to a rather large program. So we have a lot of different activities. We're working in the standard program areas for quantum information science. So we work on quantum computing. Well, I mentioned that already. We work on quantum networking. We work on quantum sensing. Some of the work that we do is on fundamental science. And so the fundamental science is often covered with work that we have with joint institutes between NIST and universities. So for example, I'm at JILA, the joint institute between NIST and the University of Colorado in Boulder. It's across the road from NIST. We do foundational science at JILA. We work on quantum standards. I'm not going to talk about those today. We also work on workforce development. The joint institutes do workforce development. We see that as a critical thing. We work on enabling technologies. So I'll tell you about some of those things today. Laser systems, for example. And we have industry partnerships, the Quantum Economic Development Consortium. NIST established the Quantum Economics Development Consortium in response to the US National Quantum Initiative. Okay, so we have a broad program. So that's the summary of NIST for its quantum information science program. So now I'm just going to give you a few highlights. There are many that I could have covered. I just picked a few that I hope that you'll be interested in. So we worked on, as I mentioned before, Dave Wineland's group began quantum information science and quantum computing with trapped ions. We still work on trapped ion quantum computing. We have a number of different projects we're working on. So here are 3 different ones. We work on the quantum CCD architecture. So we've heard a little bit about that in yesterday's talk. We work in quantum CCD where we have more than one atomic species. We think that this is actually a vital component that's necessary for trapped ion quantum computing. Of course, it's now being used. So NIST pioneered work on multi-species work, and we continue to develop that particular work. The key thing here is that if you've got more than one species, it enables you to do things like indirect initialization, cooling, and readout, and so forth, without disrupting the flow of your algorithm. The spirit, I think, of most of the programs that we have at NIST is based on the idea that we want to work on technology that we think the companies are going to need. So it's not that the companies, they sometimes are working already on these aspects, but we are trying to sort of, say, push limits in certain areas in ways that we hope that they will find helpful. So for example, in trapped ion quantum computing, one scheme that we're working on is this one in the middle, triangular 2D array. So this is a different approach to the standard quantum CCD approach. So I'm showing you a diagram here of a trap where we have 3 ions trapped in a triangle, and we can couple those ions together. So if you can design an arbitrary 2-dimensional structure of ions, and by coupling these things together, this is an ideal system for looking at quantum simulation of spin systems. So this is one system that we're working on now. This is a collaboration with Sandia National Lab. They did fabrication of the trap for us. Another system that we're working on is laser-free quantum gates. We heard a little bit about this yesterday as well. So the idea is that spontaneous emission limits the fidelity that one can achieve with laser-based gates. So one solution to that is get rid of the lasers. And so one can use an oscillating magnetic field gradients to produce spin-dependent forces that are required in order for making gates. So it's the same physics as you would have with lasers, except that one is now using magnetic fields, RF, microwave magnetic fields, and so forth. We've already achieved Bell state fidelities with these laser-free gates that are comparable with the very best laser-based quantum gates. So they work extremely well. We've also worked on other related technology that we hope to integrate into our system. So for example, here's a picture of a superconducting nanowire single photon detector that's actually integrated into a trapped ion trap. So this replaces the complicated optical schemes that one typically uses for imaging and measurement of ions. It's a detector patch that picks up the fluorescence of the atoms. And so the challenge here is integrating the fabrication technology that you need in order to make these high-performance single photon detectors into the same technology that you would use for making these surface electrode traps. We work on superconducting quantum qubits. Some of you may know that some of the very first superconducting qubits were developed by John Martinez and colleagues when he was at NIST. So we work on Josephson junctions. One of the recent projects that we've worked on with Josephson junctions is to try and improve connectivity in these systems. So in this particular example on the right, what we have is an integrated switch built into the system, which can be used to either couple qubits together. So if we want to interact with qubits for performing information processing, we can couple them together. If we want to continue the algorithm in some way where we decouple them, we can decouple them with the switch. We can also use the switch to connect qubits to readout. And so this improves noise performance and gives architects a different tool, if you like, and flex in the way in which they can design their systems. We also work on superconducting amplifiers, and so a recent example is that we've developed a field programmable Josephson amplifier, and so this system enables you to apply microwave fields to produce a drive to program what that amplifier actually does. Part of another aspect of the superconducting program is to work on photonic links to avoid the situation of having an enormous number of coax cables. So that's another piece that this team is working on. We work on nanomechanical devices, so we're really studying the macroscopic quantum states of motion with these devices. So these are tiny drumhead systems that I'm showing you a picture of. We recently demonstrated deterministic entanglement between these nanomechanical oscillators. These are the kind of systems that can be used for quantum-limited force and displacement sensing, for example. We also use the same technology built into optical systems for doing transduction. So from microwave to optical transduction for, say, quantum networking with superconducting systems. So these are tools that we are part of part of the toolbox for the kinds of applications that we want to look at, sensing and networking, for example. Another system is we work on neutral atom systems, so optical tweezer arrays, these combined tweezer technology with quantum gas microscopy, as well as high precision spectroscopy. There are many applications of this particular technology. We work on quantum metrology, so we work on an alternative architecture for building clocks. So we heard about beautiful work in Japan on optical atomic clocks. This is using tweezer arrays as an alternative to optical lattices. It gives a different kind of flexibility that one can use in the design of optical atomic clocks. We can also do many-body physics, quantum simulation. We can prepare arbitrary configurations of atoms to study different interaction systems. And of course, we're working on quantum computing with these things. So again, the idea is to develop the technology to support the companies that are developing using, for example, tweezer arrays for developing, say, quantum computing. Of course, we work on optical clocks. I mentioned that before. So this is an overview. I could produce many slides for you on optical atomic clocks. I'm only picking 2 today. So in one work that we've been doing is we've been comparing optical clocks. So we have 3 of the world's very best optical atomic clocks based in Boulder in Colorado. One of them's an aluminum trapped ion system. Another one's a ytterbium optical lattice. Those are based on the NIST campus, and then 1.5 miles down the road is JILA, the joint institute between NIST and the University of Colorado. It's on the university campus. And at JILA, we have a strontium optical atomic clock system, this Junyi's optical atomic clock. We can make comparisons between these 2 different systems. We have an optical fiber link between the 2 institutions, and we've also demonstrated free space optical connections for clocks. And so what we've done most recently with this is perform frequency ratios between these clocks as some of the most precise measurements that have ever been made. This work on developing clocks, comparing clocks and so forth, as we heard this morning, a big part of that, or a big motivation for that, is redefinition of the second. We think that a lot of important science and technology is going to come from redefinition of the second. This technology is also being used for stabilization, say phase stabilization, for quantum networking systems. And of course, we're also using these kinds of clocks as sensors. Again, we heard about some of this wonderful work being done in Japan on this, for looking for physics beyond standard model physics. So for example, dark matter searches and so forth. We're also interested in portable optical atomic clocks. I think one of the challenges in the United States is that the distances between the places that we might want to connect are very large. That means that the cost of running fiber between these places is very expensive. So one solution to this is develop portable atomic clocks. So you can see there's a picture here that's on a scale of about this big. We have already had a system you can see on the right that's been transported. It's crated up. It goes on commercial transportation, FedEx, UPS, that kind of thing. We've sent this clock to the Navy to compare with their optical atomic clock systems. And so we see this as an important way of being able to make clock comparisons without having to build very large distance optical networks, which is a challenge in the United States. Okay, switching gears a little bit from clocks and quantum computing, we've worked on, we have a system, we do work on Rydberg atoms, using Rydberg atoms as atomic sensors. The goal here is to replace classical RF antennas with atoms. The nice aspects of this is that the work is often directly SI traceable, and it self-calibrates. We can work with RF detection over an enormous frequency range, from megahertz to terahertz. If we are doing AM/FM detection and receiving, then one of the nice features of this is that the atoms actually perform the demodulation and down conversion functions for you. You don't have to build electrical circuits to do this as well. And there are many other applications of Rydberg systems. So I mean, quantum voltage measurements, waveform analysis, and so forth. So we have a broad program on Rydberg atom systems. We work on chip-scale atomic devices. So NIST has very nice clean room facilities which enable us to microfabricate systems. For many of the systems, in order for them to go from the laboratory into practical situations, they need to be a lot more robust than they are right now. Miniaturization is a key part of that. So here are 3 examples. There's an atomic beam clock. You can see it's rather small, about 1 centimeter across. We work on atom interferometers, inertial sensors, and so forth. and we're building next generation chip-scale atomic clocks. So before we had small but macroscopic optics that we were using for this kind of work. Now we're building with integrated photonics. So this is taking large-scale systems that with very, very high performance, miniaturizing to achieve performance that's useful for practical deployment, getting robustness. So I'm going to finish up here with a couple of other things. One of the things that NIST works on is post-quantum cryptography. I don't have slides on that today. It's a standards development for the anticipated full-scale fault-tolerant quantum computing's ability to disrupt public key encryption and so forth. So you can go to the NIST website and find out about the post-quantum cryptography program. It's a classical computing program. It's an international effort to develop a standard. They've published candidates already, and we hope to complete that in 2024. But the thing that I'm going to finish on is the Quantum Economic Development Consortium. So NIST's mission is to connect with industry. I've told you about a lot of research that we do, including some very basic research, but fundamentally what these programs are designed to do is to build innovation, is to drive innovation. So in the National Quantum Initiative Act, NIST was charged with responsibility for standing up an industry consortium. So we did that in 2018. So the goals of the consortium are to identify use cases. We've heard a lot about this work together, to try and build consensus on use cases, to identify strategic gaps and develop ideas for addressing these particular gaps. So this might be enabling technologies, workforce, and so forth, to inform the government and the private sector and investors, for example, about the kinds of both the opportunities and the challenges, to provide a sort of a community resource of information for say, the government as it makes policy decisions about what's going on, and of course to facilitate collaboration, to get people in the room and get them talking about what they're doing. It's an enormous challenge because the consortium involves enormous multinational systems integrators, some of which are here at this meeting, all the way down to one or two people who've got an idea and hope that that idea is going to transform the industry. So it's a big bridge to span. One of the things that the QEDC does is it produces information that people can use. So for example, we run workshops, so we might identify a gap, and we would run a workshop on that gap to get ideas from the community about where they see the problems and where they see the opportunities. Usually with these workshops, we then write reports, and sometimes those reports will then inform subsequent programs, like research and development programs that might be done in collaboration with NIST. It might be other government agencies that look at what the QEDC and its industry members are doing and adjust their programs. So it's a way for industry to have a voice in the community that we're building. So we generate lots of reports. And finally, with QEDC, I'll mention that the QEDC is an international thing. We recognize the critical aspect of quantum as a global thing. In order to be successful with quantum, one needs to engage on a global scale. So we do. So at the moment, we're expanding the number of countries where we accept membership applications. And of course, we have Japan. Japan, we partner with QStar, so it's very nice to be here. And we're looking forward to further collaborations. And so I'm going to just finish up here just in 30 seconds by just pointing out some of the future directions at NIST. I don't think these are really great surprises for the kinds of things that one would work on. We're a measurement science institution, metrology, that's what we do. So we are developing metrology of high fidelity systems. Well, we've been doing this for a while, but I think now the focus is on larger systems, understanding the behavior of larger systems, not just 1 and 2 qubit gates, understanding more connected systems and so forth. One of the things that's nice about NIST is we work on a whole bunch of different platforms. I told you about some of the ones that we're working on here, not all of them. And so we have the ability to both leverage these different approaches from different systems and so forth, but also to get ideas about how to make improvements. We have a reasonably large materials properties program, and so we want to leverage that to make direct scientific connections between material properties and quantum system performance. We feel that this is important for improving systems. And then the final thing that we're working on is, well, of course, we promote technology transfer. We see quantum engineering as an important gap, at least in the United States. So we have fundamental science. Engineering is the next target for collaborations with NIST. And with that, I am done.